The Easy Drawer, a drawer lift mechanism designed by Brandon Anderson, Sebastian Cheney, Eric Hackstrom, and Giovanni Zaccani.
The purpose of the Easy Drawer mechanism is to make items in lower cabinets more accessible to a person by automatically lifting a drawer and shelf closer to table height. Many kitchens around the world have at least one or two drawers located close to the ground, or even just cabinets close to the ground that for many individuals are hard to reach. The design mostly targets the elderly and disabled individuals, but any person could use the Easy Drawer to make lifting and organizing items in the drawer much easier. The Easy Drawer design also incorporates sonar sensors as a safety feature, as you can see by Gio demonstrating. There are also limit switches to ensure the mechanism stops in the correct position. The kinematic analysis for the Easy Drawer design required all of the link lengths and specified angles of each link that were found using SOLIDWORKS. The Easy Drawer was analyzed in a few different positions to gather the angular and tangential velocities and accelerations of each link. To calculate the position, velocity, and acceleration equations, a 5-bar vector loop was derived as shown. This 5-bar vector loop included the downward link arm of the parallelogram 4-bar link, the drawer, both toggle links, and the ground link. The drawer and ground link were omitted because their angles remained fixed throughout the entire motion. Once the equations were formulated, Excel was used with a guess and check method. This allowed the team to calculate the appropriate parameters of each link, which would then be used in the force analysis.
The Easy Drawer is driven by two linear actuators that exert a 100-pound force on the toggle links attached to the drawers. The drawers are sustained by both the toggle links and 4 links attached to the top of the main cabinet structure. And here's the Easy Drawer ready for action.
The purpose of our force analysis was to help us determine the size of our actuators. We perform our analysis on this position when the assembly is approaching its fully deployed state. While fully deployed, all forces are carried through the toggle bar, and in early stages, the assembly is in a natural rest state. This position is the logic choice for this analysis. A free body diagram is created to display all forces and position vectors. Using the kinematic analysis as a tool, we derive force and moment equations for all links. Force equations are then plugged into a matrix, and using Excel, we solve for our forces. Our results show that approximately 50 pounds are needed from our linear actuators. With the analysis neglecting friction from pins and determined to design a sturdy and effective prototype, we apply a safety factor of 4 and conclude that 200 pounds will be needed from our actuators. We go forth with purchasing 200-pound linear actuators.
For the stress analysis, we determined from 5 different mechanism positions that the toggle link attached to the linear actuator, which is circled in red, experienced the greatest forces and most dynamic forces throughout the mechanism's motion. At a minimum, we wanted a safety factor of 2. Our endurance strength for the stress analysis was about 10,000 psi. The 2 greatest stresses acting on the toggle link were the bending stress and tensile stress. Our total calculated stress acting on the toggle link was about 7,000 psi, which gives us a safety factor of 1.4. We found the direct shear stress on the pins to be about 3,000 psi, which gave us an acceptable safety factor of 3.6. Because of our conservative calculations, our current design will work for our prototype, but for our production model of the Easy Drawer, we would likely use cold-rolled 1018 steel, which has a much higher tensile strength, and thereby give us our desired safety factor. In conclusion, the prototype worked well and was strong enough to support a person sitting on it. Some refinement will be needed to make the Easy Drawer production ready. Finally, we would like to thank you for your time.